Hello, Dr. Omar.
Good afternoon, Saeed. How are you? How are
Good
you?
afternoon. I'm fine, thank you.
Excuse me, I in the incorrect link, but I'm not ready with you. How are you, Marcelo? How are you, Dora?
Fine, thank you for asking, Omar.
Yes.
Doing great, thank you, Omar. How are you?
It's a pleasure for me to you can join us in this session, and especially for standing up for Dr. Saeed. Welcome, Saeed, and I know that you are ready. If you are okay, we continue. We wait for 1-2 minutes more for the rest of the committee.
Yes.
Okay.
Yes, sure.
I will record the session for everyone who is not in the session. In the future, can check the record. Okay.
Okay.
Well, if you prefer, Marcelo, Dora starts at 10 or start for the seminar, and we can go ahead with the presentation. It's okay.
Sorry, what do you mean, Omar? To start?
Yes, start at 3:10 for
okay.
Start with the meeting, and obviously try to don't spend so much time for you, and we can continue with the seminar. Well, let me introduce you to Dr. Saeed Beigibourajeni. Dr. Saeed is graduate from the University of Tehran. He is a specialist in polymer technology. He also has a graduate student in the topics of technology of polymers, and he has a PhD also for the Tehran University in the same line in polymer engineering. Dr. Saeed, in this occasion, will show you the seminar Synthesis and Surface Modification of Polymers and Nanoparticles for Biomedical Applications. A brief resume of this topic, utilizing click chemistry in different applications, synthesis of dental restorative materials, surface modification of nanofillers, and photopolymerization of 3D printed resins. Using useless chemistry for surface functionalization of scaffolds and nanoparticles. Applying of hot gas chemistry to encapsulate the bioactive molecules into one resin biomaterials. So, Saeed, welcome to this seminar, and we appreciate that you can share with us your knowledge and also your experience in this topic. Go ahead, Saeed. Welcome.
Thank you very much. Okay. May I share my screen? Okay, as Dr. Omar mentioned, my name is Saeed, and first of all, let me thank you for your presence, for your time, and especially for the opportunity that gave me to present my research experience and research activities. Before to move to the main bodies of the presentation, just let me again mention some things regarding my academic background. As Dr. Omar mentioned, I hold my bachelor's degree in pure chemistry at Shiraz University, located in Iran. It's a really beautiful city, located at southwest of Iran. And then I hold my master's degree in polymer chemistry and my PhD in polymer engineering, in both in Tehran. And then I joined Azad University as an assistant professor. And in 2019, I joined Tech as a postdoctoral researcher. And for those years, I have been working with Dr. Omar, with Dr. Alan Aguirre Soto. And for the second year, I have this opportunity to work with Dr. Jaime Bonilla. And okay, my research activity is mainly related to synthesis and surface modification of polymers and nanoparticles, especially for biomedical applications. And those research activities totally belongs to three main categories: click chemistry, muscle-inspired chemistry, and host gas chemistry. And let me start with the click chemistry. And the things regarding the click chemistry, it's a terms and related to some reactions that they can make some new bonds, new covalent bonds between two different species, and they have some, they are following some criteria. They are high yielding, they have some high selectivity, they are really simple, they are eco-friendly. And the things that I want to mention here is that those reactions can produce only one product without any byproduct, or maybe just a small byproduct that can be easily removed. And that's the point for those reactions. There are many different types of reactions that have been introduced that can fulfill all criteria for those for click chemistry. For example, acid alkyl cycle addition, thiol N reaction, Diels alder reaction, nucleophilic ring opening reaction. And recently I was working on thiol N reaction. And so first of all, I want to mention shortly regarding the concept of thiol N reaction. And then I can mention some recent project related to thiol N click chemistry, click photopolymerization. And the things is that thiol N click photopolymerization can follow based on the radical mediated step growth polymerization, as you can see here in this figure. First of all, thiol functional groups can interact with the initiators under light. Maybe if we are using photopolymerization, produce a thiol radical, and this thiol radical can interact with the double bonds and then again produce a newly generated radicals, and subsequently these radicals can interact with the another functional groups, thiol functional groups, and finally it can be done for many times and produce polymers. As you can see here, I want to compare the progress of molecular weights for chain growth polymerization, step growth polymerization, and its the thiol N polymerization. Accordingly, the progress of the molecular weight for this system is the middle between the chain growth and step growth. So it's known as a radical related to chain growth, and it's the step growth polymerization. So it's a mix of combination between those techniques, and we can see different advantages for those systems. We can see delayed gelation, we have a lower shrinkage strain and stress, we can see higher degree of conversion regarding the conventional methods, and we don't have any problems with the presence of oxygen because we don't have any oxygen inhibition in these systems. And we know that in the conventional radical system, we have a bunch of problems in the presence of the oxygens, and we have all the time a tacky surface because incomplete polymerization. And we can have the more homogeneous structure, more homogeneous network for those polymers and improve fracture toughness. So the things that I want to mention is regarding my research project, and the target tissue is tooth. And the things, first of all, I want to mention volumetric shrinkage. If we have some monomers, all monomers, they have some only van der Waals interaction with each other. It's the only van der Waals interaction. So during the photopolymerization or during the polymerization, monomers can interact with each other by a covalent bond. And according to this covalent bond, we can see some reduction in the volume, and this reduction is known as a volumetric shrinkage, and it's really important, really important. So imagine that if we have a cavity of tooth and we want to put some materials in it, and the things is that during the photopolymerization, maybe some volumetric shrinkage can happen, and because okay, first of all, maybe we have some marginal gap, and the bonding of the restorative material is the material that we want to use for filling the tooth structure. And we have the marginal gap here, or interface the bonding, and at the same time, simultaneously, because this shrinkage strain can happen under confinement, maybe some stress can be generated, and it's known as a shrinkage stress. And it's the real images, it's the scanning electron microscopic images regarding the dentin structure, it's the tooth structure, and it's the material that we used for the restorated the tooth cavities, then the tooth decays. And as you can see here, we have a interphase debonding, and it's not good at all. And because there are maybe many kinds of bacteria can insert these interfaces and start to activities and produce some problems known as a secondary caries, especially if you have a restorated dental. So because we wanted to remove these things, first of all, we try to synthesize a new monomers. We use a diisocyanate monomers, and the it's the monohydroxyl group monomers that contains two different allyl ether as a photopolymerizable functional groups, and we produce and synthesize these monomers. These monomers has 1, 2, 3, and 4 allyl groups that they can undergo photopolymerization. As well, they have two urethane bonds, and this urethane linkage is really nice because they can help us for better adhesion to the system, to better adhesion to the dental structure, and they have a hydrogen bond. At the end, we use the other matrix. It's a thiol because we want to use a thiol N, and at the same time, we use this monomer as a dimetacrylate system. It's the ternary system, thiol, metacrylate, and allyl ether system. And as a filler, we try to modify the surface of the nanoparticles. It's a pus. It's a nano cages, and it's a glycidyl part, and we set a triazolium groups on the surface of nanoparticles. And the main reason that we did this, because we know that the quaternary ammonium, especially in the aromatic rings, they can show really nice bactericidal activity. They can really show us antibacterial activity. For that reason, we are using these nanoparticles that already functionalize with the antibacterial groups. So let me just mention some shortly regarding the results. As you can see here, it's the dynamic mechanical analysis test, and with increasing the thiolane content, we can see that we have a more heterogeneous structure. The first one is related to thiol N, pure thiol N, and the last one is related to the samples with lower amounts of thiol N. And it mentions that thiol N system is really nice regarding the homogeneous system. And the next one is related, the next one is related to shrinkage stress. And we can decrease the shrinkage stress with increasing the thiol content. And finally, we have the antibacterial activity. We, at the same time, we prepare and we synthesize a monomer as a model, and it's the quaternary ammonium with the aliphatic structure, and the other one is with the aromatic structure. And we can see that it's this one, the nanoparticles functionalized with the triazolium functional groups can show us higher degree of bactericidal activities, and I think it was the good result for us. Okay, based on my recent experience, already we planning for a new project. It's a collaboration between University of Colorado Denver and Technologico de Monterrey. It's a collaboration, and we have a combination between click chemistry and 3D printing. According to this proposal, we want to, first of all, we want to prepare and synthesize these monomers. It's the monomers containing allyl ether functional groups and metaacrylate functional groups. It means that we have both functional groups at a single monomer. And we want to use these monomers as a hybrid monomers, and we want to use this formulation. It's the hybrid monomer plus thiol and thiol monomers, and this one is the photoinitiator systems. After receiving the feedbacks from this formula, the next step of this proposal, the next step of this project is producing some silicone-based ink or some silicone-based resin for 3D printing. The main thing is that these days, producing of elastomeric transparent resin for 3D printer is really highly on demanding, and is really important because we need this for different applications. For example, for soft robotic, maybe for preparation of some microfluidic devices, or maybe for preparation some evaluation of optical flow visualization. So we need some transparent elastomer material based on 3D printing. For that reason, we can use the same logic as I already mentioned in previous slide, based on the different functional groups in the between, and it's based on the some silicon chains, silicon oligomers, or maybe silicon prepolymer, and we can do the same logic, do the same strategy, and adding some groups on the surface. It's the polyletter, and it's a vinyl and it's the methacrylate groups, and at the same time we can functionalize other kinds of the silicon oligomers, and we mixing those things, we will have the final structure for the inks, for the resin for 3D printing. And we want to use this one, and we already purchased all materials, and I hope so that we can start synthesis those materials maybe in 1 month. Okay, the second category that I want to mention is the muscle-inspired chemistry. And first of all, let me again shortly explain this concept. There are some marine mussels, as you can see here, and they are known as a fouling organism. And the things that they can attack and they can attach to different substrates, and to the organic substrate, to inorganic substrate, in the wet situation, in the dry situation, even those material and those muscles can attach to the some resistant to adhesion resistant polymer. For example, we have Teflon, polytetrafluoroethylene, and we know that it's known as a non-stickant polymer. However, these muscles can interact and can attach to the Teflon. So the main thing is that there are some proteins that can be secreted at the interface of these muscles and the substrate. And the main hypothesis is that there are some amino acids in the structure of proteins that they have some amine groups, and the other groups, as you can see here, is the phenolic groups. The things is that recently dopamine, it's the small monomers have already been introduced as a monomer that can mimic the structure of this interface, because dopamine contains the both amine groups and the other phenolic groups. So under the base situation at the high pH, we can trigger the polymerization of these monomers, and after oxidation, cyclization, and again isomerization, we will have the copolymerization, and it's the thin copolymer that can attach to all surfaces. Okay, it's the first concept. And what about the second concept? The second concept is that it's regarding the tissue engineering. We know that over the past decades, tissue engineering have been developed for regeneration of different kinds of the failed or the damaged tissues. The main things regarding tissue engineering, we have 3 different items for tissue engineering. It's cells, it's signals, for example, growth factors, and it's a scaffold. So the main thing is that the scaffolds play the main role, critical role in tissue engineering. And when we are talking regarding the ideal scaffold, we know that the ideal scaffold should have some good characteristics, should follow some criteria. For example, biodegradability, biocompatibility, and for example, the architecture of the scaffolds and the mechanical properties. Regarding the structure and the microstructure of the scaffolds, we know that the producing some scaffolds, some fibrous scaffolds, based on the, maybe we can use electrospinning or other techniques, fibrous scaffolds that can mimic the structure, the fibrous structure of collagen fiber embedded in ECM, extracellular matrix, is really important. Accordingly, and for that reason, many kinds of research have already been done regarding producing the electrospinning to produce some fibers and accordingly to produce some scaffolds. However, the point is that there are some disadvantages related to electrospinning. First of all, we have really low production rate. Second one, we have really low safety because we are using high voltage for this instrument. And I think the main things is that the final products based on the electrospinning is the only two-dimensional math. It's two-dimensional math, and I think it's working with this for producing some 3D scale is really hard. On the other hand, we have another technique is known as a centrifugal spinning. At the same time, it's known as a jet spinning or rotary spinning. And this centrifugal spinning is not a new technique. For many times has been used for producing, for example, glass fiber. However, the using of centrifugal spinning in the tissue engineering is really new. And hardly ever you can find a lot of those kinds of the research on this area. So the thing is that centrifugal spinning is a technique that have a good capability for producing fibers at high rates and a higher safety. And the main thing is that you will receive some 3D fibrous structure best described as a wool. As we can see here, at the same way, we can see the 3D structure for this wool. And the thing is that for the first time, we used this technique, centrifugal technique, for producing some 3D scaffold in combination by a muscle-inspired technique. And you can see here, we try to use this centrifugal spinning to produce some gelatin fibrous wool, and after that we use polydopamine to make a thin layer on the surface of those wools, and after that we produce an scaffold. According to this the short video, as you can see here, it's the recyclable compressed ability in the wet situation, and with adding, and it can tolerate the pressure and again retain the primary structure, and it's really good. The things that I want to mention, it's the roadmap that we already used to produce those kinds of scaffold. We use the centrifugal spinning. We'll have some gelatin wools. After that, we do the thermally cross-linking, and then we put a thin layer of the polydopamine on the surface because it has an extraordinary adhesion. We know, we already mentioned, that can mimic the extraordinary adhesion ability of those muscles. And after that, we molding in the weld plate, and this is, as you can see, it's the freeze-dried scaffold, and it's a 3D scaffold. And you can see it's the scanning electron microscopy, SEM macrographs of different scaffold. This one is the pure gelatins, the other one is the cross-link. This one is the containing a layer of the polydopamine. This one is the after molding and after freeze drying, and this one is the samples containing polydopamine. And as you can see here, all samples have the long and continuous structure, fibrous structure, and it means that during the preparation of the scaffolds, we don't have any significant changes regarding the structure. The other things that is that we did proliferation of the HDF cells on the surface of those scaffolds. And as you can see here, after 7 days, we have a significant increases in the amount of the cells. The black one is related to the pure gelatin, and the gray one is related to the gelatin containing a polydopamine coating. And as you can see here, the samples containing a polydopamine coating has a significant increase in the amount of cells. The other thing that is really interesting is regarding the histological properties, and it's the Dappier-Stein cross-section of the cell-loaded scaffold, because we wanted to know how much those cells can penetrate, can insert, can infiltrate in the final scaffold. And it's really important because it's the main steps for regeneration of the tissue. So as you can see here, these dots is the sign, is already stained by a DAPI, and they are a sign of the cells. And as you can see here, the scaffolds containing the polydopamine coatings have a higher amounts of the filtration of cells, and it's because of the presence of the polydopamine, and because it's the extraordinary adhesion ability. So according to the recent activities, At the moment, we are working on a proposal. It's a project. It's a collaboration between Technological Demontre, University of Zurich, located in Switzerland, and Azad University, located in Iran. And we want to plan for a project. Already we are writing the proposal for. It's the combination between muscle-inspired chemistry, centrifugal spinning, and 3D printing. And the main thing that I want to mention here, this project is related to patient-specific scaffold. We know that tissue engineering has been extensively used to regenerate the damaged tissue. But the main thing is that, for example, if a person has some problems regarding the mandible, has some perfect regarding the bones, other parts of the body, I don't know, maybe other tissues, other target tissue, the main thing is that we can produce some patient-specific for that person, especially for that person, and it's known as a patient-specific. And so producing some patient-specific scaffold based on the fibrous structure is still demanding, and we want to do that regarding this proposal. So accordingly, we are mixing indirect 3D printing to producing some anatomically shaped mold, and after that we use centrifugal spinning, and finally we used a muscle inspired to put a layer on the surface of the scaffold to prepare those things. And here I put the title of the project, and it's the roadmap. First of all, we received a CT scan or MRI from the patient regarding the target tissue. After that, we have the image processing or image segmentation. After that, we use some softwares to plan and to design the anatomically shaped mold. And we do it with the 3D printer, SLA or maybe FDM. It depends on the raw material. After that, we use that mold, and we use those walls that's already coated by polydopamine and molding, and finally we will have the final structure for those parts that have some problems. And in continue, we can do in vitro and in vivo analysis for those techniques. As I mentioned, it's a collaboration between Technological Demontre. We can use the 3D printer here, and we can use some preparing some monomers here. After that, we receive some images from the Switzerland, and they can put some image analysis for us. And we try to do in vitro and in vivo tests in Iran regarding those scaffolds. And the next category is related to host-guest chemistry. When we are talking regarding the host-guest chemistry, is the new, it's not new, it's the fantastic approaches based on the some non-covalent interactions, and we can use this technique to protect some molecules, especially biological molecules that can be used in the pharmaceutical or maybe preclinical things related, because we want to protect those biological molecules for better interaction, and maybe for the releasing at the time that we want to do that. So curcumin is a material that we already used it. It's the new project that we already did it. And the things related to the curcumin is a bioactive molecule. It has two different two phenolic groups. And the main things related to curcumin, it can show anti-inflammatory, antioxidants, and antibacterial activities. However, we have some restrictions regarding using curcumin because of the hydrophobic structure of curcumin. So curcumin can show only poor bioavailability, especially, for example, if we are using this molecule for the wound dressing at the wound site, we have some problems with this molecule. Accordingly, the other things, if we are, for example, some functional groups, for example, if we have some isocyanate functional group, we have some problems because imagine that we want to produce polyurethane, and we know that the polyurethane can be synthesized based on the isocyanate group and alcohol group or hydroxyl group. The thing is that if we want to use polyurethane as a matrix that is really usual, especially for wound dressing system, we have some problems. And the thing is that these isocyanates can interact with the hydroxyl group, and we want to prevent these things. So for that reason, in the recent project that we already did, we used the secondary host gas complexations to protect the hydroxyl moieties of curcumin. It means that we use two different hosts. One of them is the primary host. The second one is known as a parent host. And accordingly, we can protect those hydroxyl groups and the whole structure of these molecules. So imagine if we are using this system, it's the diisocyanate monomers, it's the dihydroxyl group monomers, and we want to produce polyurethanes as a final polymers. We don't have any interference with the interaction between these hydroxyl groups and isocyanate groups. So accordingly, we did a project. It means antibacterial polyurethane nanocomposites wound dressing. We want to use the polyurethane, elastomeric polyurethane is based on the essential oil is based on the castor oil, and accordingly, we want to use the curcumin to enhance the healing of the wound, because the final application of this nanocomposite is for wound dressing. So accordingly, we use two different things as a parent host and as a primary host. First of all, we use sulfonated calixarin. It's this shape, as you can see, it has a basket shape. We can use this one, and we can put the curcumin in it. And after that, curcumin can insert inside of this basket as a primary host. After that, and as an in situ production, we can produce some LDH nanoparticles. It's the layered double hydroxides nanoparticles. And the things is that we want to intercalate it and send this primary host with curcumin. We want to send it between the layers of the LDH, so LDH can protect against some isocyanate groups and other things like that. So it's known as a secondary host gas complexations. You can see XRD analysis for those things. For example, for the LDH, DS spacing is about 7.7. However, for the secondary carriers host gas is about 13.7. It means that, okay, it's the LDH can be already intercalated by those structure of the calixarin, and it mentioned that we can we can do it. And the other things is the test regarding the bacterial inhibition zone, because as I mentioned, we want to use the curcumin as an antibacterial agent, and you can see here that I already put the different codes for different materials. PU is the pure polyurethane, PU, LDH is the adding nanoparticles of nanosheets of the LDH without any modification. After that is the only LDH and curcumin without using the primary host, and the last one is the secondary host gas complexation. And you can see we are according the inhibition zone for both bacteria is the gram negative and positive for both. So you have a better results regarding these samples that it mentioned. Okay, we have a really nice and high concentration and high bioavailability of the curcumin in this regard. The other things that I want to mention is the histological assessment, because we did an in vivo test for this technique, for these secondary host gas complexations, and it's regarding the epidermal layer formation. And according to the, as you can see here, according to the H and E staining, we can see the formation of the epidermal layer, and also we can see a lot of the follicle of hairs, and it mentioned that we have the really nice healing in comparison of curcumin. The other thing that I want to mention is that again, when we are using the host guest chemistry, it's really good. However, as I mentioned, it's based on the some non-covalent interactions. So maybe host gas can is the reversible equilibrium. So maybe we can see some reduction in the efficiency of host gas interactions. And if we want to solve this problem, we can use the multi-cavity host, and it means that we can produce some multi-cavity that already covalently interacted with each other. So we have a bunch of curcumin that's already separated and already incorporated inside of those baskets, and we can use those systems for the as a multi-cavity as a new host for those things. For that reason, we did another projects, and we are doing projects because we already only do the first step, and accordingly we used isocyanate functionalized cyclodextrin. We functionalize the surface of this cyclodextrin based on the isocyanate, and after that we add uh, another host. It's known as a sulfonated calixarin is the usual host that we can use for these techniques. And accordingly, it's the interaction between hydroxyl group and isocyanate group, and we have some urethane linkage, and we produce a multi-cavity host for these applications. And after that, we loaded these multi-cavity hosts inside of the alginate gels and produced some wound dressing again for different applications, for example, for skin wound healing. And I put some results regarding the cumulative release curve of the is related to release of the curcumin. As you can see here, there are again different types of the samples. Is the alginate curcumin, is the alginate only cyclodextrin, the other one is the alginate and only the presence of the single hole of the calixarin. The fourth one is the combination between the two different calixarins, sulfonated and non-sulfonated, and the last one is this one, is the interaction between cyclodextrin and sulfonated calixarin. And as you can see here, the best results is regarding this multi-cavity host, multi-cavity microcycle host. And after 72 hours, as you can see here, we have approximately near to 80% release of curcumin, and it's really nice. It's really good because we know that the curcumin has a hydrophobic structure, and we all the time we have some problems regarding the bioavailability of this material and we have some problems regarding releasing. And the other hydrogels, as you can see here, other hydrogels have less than 10% release, less than 10% release. And this is really important because when we have, for example, some wound on the surface, the first step is stop bleeding. And for that reason, undoubtedly the presence of curcumin can help us, because we know that the high concentration of curcumin can help us to stop bleeding. And for that reason, it would be good results for us. The other things, we again did antibacterial evaluation, and as you can see here, the first one is only alginate containing curcumin. The second one is the alginate that curcumin already incorporated in this multi-cavity host, and you can see here that's about more than 20% we can see increase in antibacterial activity, and it's because the using of this multi-cavity can enhance the efficiency of the host gas interaction. So it's the last part of the research structure is the collaboration between Dental School of Monterey and School of Engineering of Science of the Technological de Monterey, and we are going to build a shrinkage strain instrument for them, because when they are working in the dental school, they have some problems and they want to measure the shrinkage strain. I already mentioned it earlier in the presentation. I mentioned that if you have some monomers, first of all, they have only some van der Waals interaction, and after polymerization, they have some covalent interaction. The thing is that we can some reduction in volume is known as a volumetric shrinkage. And it's really nice if we can measure this one. And so accordingly, we want build an instrument, as you can see here. This instrument is based on some LVDT to control the shrinkage, and after that we have a display and we can show the shrinkage strain. And it's a collaboration between dental school and the School of Engineering. And it's the last slide regarding some industrial project. We are doing some industrial project. The first one is regarding the Allen company. I think it's the Allen company located in Monterey, and producing some gels, sanitizer gels. And the project is that we are enhancing the stability of those in the sanitizer gels. And I'm working under supervision of Dr. Jaime Bonilla. And the other projects is the collaboration regarding with Dow Chemical Company. We are characterization of some polymeric compounds, and the leader of this project is Dr. Hector Alan Aguirre Soto, and we are doing those things. Okay, thank you for your time, thank you for your attention, and I'm really happy that I have this opportunity to share my research activities with you, and it would be great if I can receive your feedback. Thank you very much.
Thank you very much, Dr. Saeed, for your presentation. And we have a small time for some questions. Please, Dora, please, Marcelo, if you have any question for Saeed, go ahead. We have some minutes.
If you want to start, Dora.
Can you hear me?
Yes, we can hear you.
So thank you very much, Saeed, for the presentation. I like it very much. I think it's a very good explanation for all the process and the chemistry. I see that you manage chemistry very well. So I have just a couple of questions. So you mentioned the alginate hydrogels.
Yes.
So myself, I have worked more with PVA hydrogels. So I was wondering if, can you tell me a little bit like the difference of these two materials?
Yes, sure. First of all, the things that regarding the alginate, we need to use, for example, calcium chlorate, because we need some calcium cations to produce some physical cross-linking between the polymer chains and producing the gels. However, when we are talking regarding the PVA, because it has a bunch of hydroxyl group, however, it depends on because we can buy PVA, polyvinyl alcohol, as the hydrolysis acetate groups. So it depends on the concentration of the hydroxyl groups. So because it has a bunch of OH groups, hydroxyl groups, for producing the hydrogels, we don't have any problems. I mean, it's again some physical cross-linking based on the hydrogen bondings between the polymer chains.
Thank you very much, Said. And from the
You're welcome.
From the mechanical part of these materials.
Regarding the mechanical properties, I didn't work with the PVA as a hydrogel, but I think maybe alginate has a better maybe strength or young modulus, because we are using some calcium chlorate for producing some physical cross-linking, I think.
Thank you, Said. Said, have you read something about like the roughness of this material, this hydrogel, or?
No, I mean, we didn't do any experiments regarding the roughness, and because most of the test is regarding the antibacterial activities, regarding the cell viabilities, and for the dose system that contains some nanoparticles, only did some XRD FTR for the analyzing the systems. However, if we want, we can use the different techniques. For example, we can use AM atomic force microscopy to study the roughness of the surface. However, if we want only the morphology, we can use a scanning electron microscopy, but I think if we can use the AFM, we have the better result regarding the roughness of the surface.
Okay, thank you very much, Said.
You're welcome.
Yes. So
Thank
can
you.
you tell me a little bit? Can you tell me a little bit about the processing of this material?
Yes, which one? This one, the first one, you mean?
Alginate hydrogens.
Yes. First of all, because it's the in situ forming of the alginate hydrogels, first of all, we prepare a solution based on the alginate. After that, we add those multi-cavity microcycles that containing and already incorporated with the curcumin, and we put on the ester for overnight for a better mixing, and after that, we use the ultrasonic, and after that, we add some calcium chloride, and after at a short time, you can see the gels, and it would be the hydrogels. And we use those things in different formats. First of all, in the newly generated hydrogels, and also we freeze dried those gels, and we prepare the solid frame and solid structure of those systems, because we wanted to know what happened exactly, especially for those tests. For example, for using as an antibacterial, or for the cell viability, we use those format as a newly generated hydrogels and the freeze-dried hydrogels.
Thank you, Said. Said, do you make any, like for example, to monitoring the rheology of this solution? Are you interested?
Yes. We at the moment we are doing, because as I mentioned, at the moment we are doing and we are continuing, and we want to do the frequency sweep and the temperature sweep to know, okay, what happened exactly at the gel points, and regarding some extracting some mechanical properties in this regard.
So any specific value that you are interested to check in order to get this hydrogen in a specific conditions site? Or
Regarding the rheological study, you mean?
Yes. Like for example, I don't know if you check
Yes. We want, because we want to check the gel points, especially we want the check the gel points, and also we want to know the effect of the temperature. For that reason, we want to do it as a temperature sweep at a different temperature. Maybe what happened exactly, under which condition we have the faster gelation, because it's really important for us. We know that if we add only some calcium chloride, undoubtedly we have a really just maybe after some minutes. This is really fast. However, we want to know exactly what happened at different temperature, and exactly we want to study the gel point.
Thank you, Said. Said, if you have a graph where in your x-axis are temperature, and in the y-axis is the modulus, the viscous and the elastic modulus. How do you expect this behavior?
Okay, my expectation is that I can see an increasing in the modules of the systems.
But how is the elastic with respect with the modulus, the viscous modulus, the elastic with the viscous modulus?
Okay, first of all, I think as I mentioned, for the young modulus, it's related to young modulus. However, regarding the last one, we can see an increasing trend, and after that is the level of, for someone, it depends after we passing the gel points, we can see a level of in the curve.
Okay. For example, if like let's think that you have, like for example, lower temperature, I don't know, like 20 Celsius, for example. So how would be the elastic modulus with respect to the viscous modulus? For example, at 20, and how does it behave differently, for example, I don't know, 160 Celsius?
Okay, you mean that if we want to, if we have a curve and in y-axis we have the elastic, sorry,
Yeah, my connection is not
up.
very good. Hello?
Yes, so if we have a curve and in x-axis it's the elastic modulus, yes?
Yeah, like in the x you have temperature. For example,
In the x,
yeah, you have
so,
temperature.
okay, if I
And in the
if
y,
I undress,
can you hear me?
yes, but it's a little bit
Yeah,
breaking up. If
yeah,
I
my
undress,
connection is not very good. Yeah, in the
if I If I understood your question very well, maybe we can see a decreasing trend regarding the versus temperature. Again, it depends if we want to study those points before gel points or maybe after gel points. It depends in the end, we can have some big significant effect for those data.
Yeah, maybe we will need like to make the experiment, right? Like temperature sweep. Well, thank you very much, Sadid. And just one more question. Like this curcumine material, it sounds very interesting. And I was wondering, and I was wondering, why is this material your primary choice? Is because of the biocompatibility or the chemical stability?
Yes, exactly. For the chemical stability, however, there are some concerns regarding the chemical stability. For that reason, we are using the Huskies to protect this molecule. However, it's the cost effective and it's really nice. And the main things is that the other researchers already reported that they had really nice results regarding the preclinical applications for the curcumin, because we have a bunch of other materials which can be used as antibacterial agents. However, most of them maybe you only can be used at the laboratory. After that, when you want to use it in a real situation, in vivo situation and preclinical situation, they cannot show a good results. However, curcumin has been used extensively, especially in the preclinical situation, and we received many good results in this regard. For that reason, we already choose the curcumin as the active molecules.
Thank you very much, Sadid. And
You're
one more
welcome.
thing, like
Yes.
it sounds very interesting, the centrifugal spinning.
Yes.
And so, like, how much material can you get by this method?
Okay, the main things is that in comparison with the electrospinning, for example, if you want to do electrospinning for a solution, for the gelatin solution, maybe you need it depends on the material. For example, for gelatins, maybe you need a 15% weight percent. However, if you want to use the centrifugal spinning, you need the solution with higher concentration, maybe around 40 to 45%. That's it. And the other things for producing and for the production rate is really high. I remember that when I did it, because I did it myself, I can produce many for example, let me show you according to this picture. For these samples, I can produce more than 13 scaffolds after only one running of the centrifugal spinning. And those scaffolds already prepared at the 24 well plate.
So can you make can you make some orientation of these fibers? Have you tried?
I didn't myself. However, I know that yes, it's possible and it can be controlled based on the direction because you have some nozzles and centrifugal forces, and we can do it. However, undoubtedly, you will have lower production rate. But yes, it can be, it is possible.
Thank you, Said. That's all for me. And
You're welcome.
congratulations
Thank
again.
you.
It's excellent presentation, and I think like everybody can understand. You explained very well. So,
Thank you very much. Thank you for your presence.
congratulations.
Thank you for your time. Thank you.
Thank you, Dora. And we continue. We have time for Ms. Marcelo Lozano. Luis, you have any question for Dr. Said?
Yeah, I just have I have just a few questions, mostly regarding with the manufacturing processes, specifically centrifugal spinning, because it's a very interesting process. You presented centrifugal spinning as a green process, and I agree, as long as you use the right solvent. What is the solvent you use for preparing the fibers?
Sorry, could you please? Yeah, I can hear you.
My question was, what is the solvent you use for?
Oh, your solvent. The solvent is a water.
Okay.
And the things is that help us because we don't have any problems with the other materials. Yes.
Yeah, that's right. Are you interested in modulating the diameter fibers?
Yes, and yes, it's really important, and the things that we want to do it and continue working on it, because the main things, let me move to these images according to this SCM regarding the diameter of fibers. We try to produce really a small distribution of the diameters of fibers. However, it's as I already mentioned, it's really hard to control the diameter distribution and as well as the direction and alignment of the fibers. And yes, we want to work on it. However, again, I didn't work on these things because we were using a small centrifugal spinning, and that we built up ourselves. I mean, we didn't buy it from the company, and for that reason, maybe we need to check some things and some parts.
Okay. If that's the case, that you want to modulate the diameter of the fibers, were you looking for smaller diameter, greater diameter, below certain range, below certain microns, or what would be looking for?
Undoubtedly, we are looking for a smaller diameter in the for fiber, because things regarding the electrospinning, it's possible with electrospinning that we produce some real nanofibers less than maybe around 100 nanometers. However, the things regarding the the centrifugal spinning, most of the time, and the smaller diameter that we could synthesize, it was about 300 nanometers, between 200 nanometers and 300 nanometers. So we need to produce some fibers with the smaller diameters.
I see. You mentioned here in this slide wools, that you can get wools from centrifugal spinning, and that creates certain mechanical properties when you pushing, right, the scaffold. Does that mechanical properties are obtained because of the amount of material? You have a wool and you put it there, and that's the reason why you have that mechanical properties, or there's another reason?
Yes, it's a really nice question, because we were facing with this one. The things is that we already used polydopamine as a coating here, and let me, okay, I have some, let me move, I have some backup slides I can show you here, this one. These things exactly happens between polydopamine and gelatins, because we know that gelatins have some amine groups, And we know that the dopamine have some phenolic groups that under oxidation can produce the other groups, as you can see here. Accordingly, there will be two different kinds of interaction, Michael addition and shift-based reaction. And accordingly, so we know that the dopamine can really have a good interaction with the surface, and the things that we already mentioned, that is the higher amount of mechanical properties in comparison with the pure gelatins. If you have pure gelatins, you have already coated with the polydopamine. Undoubtedly, the second one, coated with polydopamine, exhibited higher mechanical properties and reducibility for the compress, recompress, compress, recompress, and because the presence of the polydopamine.
Okay, I see. This is very interesting, that process. I think get very clear in the project. You mentioned the muscle inspire project. I think what that was in that project. How are you planning to combine the centrifugal and spinning with the 3D printing? It's not that you are going to use the fibers, right? In the 3D
yes, this
printing.
one, yes. Yeah,
yes.
We are using indirect 3D printing. I mean, we are only using the 3D printing to produce some mold, and the mold exactly based on some MRI that we receive from the patient. So we can produce some anatomically shaped, and it's a patient specific, related to the specific the patient. After that, we can use the indirect 3D printing to build this mold. After that, we use those fibers already coated with polydopamine and molded inside of the mold. However, the main thing is that we can use two different molds. Maybe it's the removable molds. For example, we can use PVA. Well, I can buy PVA, and after that, using the FDM as a melting for the melting those material and producing some mold based on PVA. And we know that PVA can be dissolved in water. So we can use the sacrifiable mold, and after that remove it, and we will have only this scaffold. On the other hand, we can use some permanent mold, maybe based on the polyvinyl alcohol, based on the polylactic acid, poly-PCl, gelatins, and different kinds. And we can put both scaffolds and the mold both inside of the, for example, part for the damaged tissue.
So you are really creating or producing one-of-a-kind product, personalized for each patient.
Exactly, yes, exactly, yes, exactly. And we are using the 3D printer to help us, because it's possible for us to use the 3D printer. It can be connected to the different DICOM images, MRI images, CT scan images, and exactly and precisely produce the files related to the damaged tissue.
So far, you are only interested in dental processes, dental parts, but it can be extended to other.
Yes, sure. Yes, yes. The main things, because we have some collaboration with the University of Zurich, and the other professor who working there is working on those things. Is working on the dental materials, and she mentioned that she can help for providing DOM images and help us for maybe after that for in vivo test. And for that reason, we try to plan for this part. However, as you mentioned, it can be possible for other parts, for other target tissues.
Let's see. And I have one last question in your slide 24. If you can go to that one, please. I see from the XRD results that it seems that the crystalline structure is lost. Will that affect your performance or in the application you're looking for?
Yes, the main things, no, that we only use the XRD because we want to know what's happening exactly with the, okay, is it possible for intercalation, and where is the location of the curcumin and the calixarin? Is it between of the sheets of the LDH or no? And we use XRD, and as you can see here, it's the 2003 is a peak related to the LDH sheets. And when we use this multi-cavity, no, not multi-cavity, it's the, forget the name, it's the curcumin incorporated in calixarin host. It's not removed, just moved to lower degree. As you can see here, it's here, and it means that we can increase the space between the sheets, between the layers. Accordingly, I already mentioned it's the de-spacing is related to the distance between the sheet lights is about 13. However, for the original LDH, it's about 7.7.
I see. So the crystalline structure is not really an issue or concern for you.
No.
Not for the application. I see.
No.
I remember I have one more question. I just want to know, I'm interested in, you mentioned that the ternary amine has
yes.
antibacterial properties?
Yes, exactly. Yes.
Why is that? What is this amine doing to
the things that can happen here is the interaction between this quaternary amine, because we know that the surface and if you have some microorganism, for example, if you have some bacteria, the cell bacteria has some negative points. And accordingly, if I have some quaternary ammonium with the positive charge, they can interact with each other. However, the main things, if you have two different structures, this one as a model, it's the aliphatic structure. However, the other one is the quaternary. Both are quaternary. This one is the aromatic structure. And we find this, that if you have aromatic structure, the positive charge can resonance in the ring, and accordingly is the localization of the positive charge and the better interaction with the membrane of the bacteria, the membrane of the cell. And for that reason, we can see antibacterial effect.
I see. Very interesting. Okay, thank you very much. Very interesting. Your topic and your presentation, very well explained. Thank you so much.
Thank you for your time. Thank you for your presentation.
Thank you very much, Luis. Thank you very much, Dora. While we finish this seminar, we appreciate to Dr. Luis Marcelo and Dr. Dora Liliana. You can fill in the Google form for trying to access this seminar, and we appreciate all your comments and evaluations. So, Saeed, thank you very much for your time, for the presentation. They were very interesting, very clear, and we hope in the future we can collaborate with the Tec de Monterrey. In the name of the Department of the Science of the Monterrey region, we want to thanks to Luis Marcelo Lozano, Doriana Medina for your time, for all your contribution, and we appreciate all this effort for being in this session. Thank you very much, Dora, Luis.
Thank you, Omar. Thank you, Saeed. Thank you, Luis.
Thank you, Dora.
Thank you very much. Thank you for your time. Thank you.
See you soon. Bye, everyone.